Let's say if we have the function ln 1 minus x squared, how can we write a power series representation of that function? The first thing we need to do is factor 1 minus x squared. And so we can write that as 1 minus x times 1 plus x. Now, a property of natural logs allows us to take a single log and express it as the sum of two logs. So ln a times b is ln a plus ln b. So therefore, we can rewrite this expression as the natural log of 1 minus x plus the natural log of 1 plus x. Now, here's a question for you. What is the derivative of ln 1 minus x? So recall that the derivative of the natural log of u is going to be u prime over u. So in this case, u is 1 minus x, so u prime, that's going to be negative 1. So the derivative of ln 1 minus x is going to be negative 1 over 1 minus x. Now what about the derivative of ln 1 plus x? So this is going to be 1 over 1 plus x. Now let's take the integral of both sides. These two will cancel, and so we can say that ln 1 minus x is the integral of negative 1 over 1 minus x dx. And if we do the same thing here, these two will cancel, and so we could say that the natural log of 1 plus x is the integral of 1 over 1 plus x dx. So let's replace this with what we have here. And let's replace ln 1 plus x with this expression. And so this is all going to equal ln 1 minus x squared. Now let's write a power series representation of negative 1 over 1 minus x. And let's do the same for 1 over 1 plus x. So this is already in the appropriate form. It's in the form a divided by 1 minus r, which is the sum of an infinite geometric series. So we can see that a is 1 and r is x. So using the power series, the geometric series in that form, we can write a power series like this. It's going to be a, which is negative 1, times r, which is x, raised to the n, from 0 to infinity. So we can say that ln 1 minus x squared is equal to this thing, but I'm going to write it later. Now let's focus on this one. We need to change the plus into a minus. So 1 plus x is the same as 1 minus negative x. So in this form, we can see that a is 1 and r is negative x. So using that expression, we have the series 1 times negative x to the n. And negative x can be written as negative 1 times x. And all of this is raised to the n power. So if we distribute the n, we're going to get negative 1 to the n, x to the n, from 0 to infinity. So at this point, we could say that ln 1 minus x squared is equal to the integral of this series. I'm going to move the negative sign to the front. and this is x to the n plus the integral of this series as well. Now I'm going to combine these two integrals into one single integral. So we can say that ln 1 minus x squared is equal to the integral of the series from 0 to infinity. Now notice that we can take out x to the n. So that's a common factor that we can pull out. And then we're left over with negative 1 to the n. And then we have a negative for this one. So we could just say minus 1. So note that if I multiply x to the n times negative 1, it's going to give me that term. And then if I multiply x to the n by this, I'm going to get this term. So what is the antiderivative of this expression? Now keep in mind, n is a constant, x is the variable. So this whole thing is a constant. Let's rewrite the constant first. So that's negative 1 to the n minus 1, and then let's integrate x to the n using the power rule. So that's going to be x to the n plus 1 divided by n plus 1. And so this is going to be the series from 0 to infinity. And we need to add the constant of integration plus c. So now we have our answer. At least this is one way of writing the answer. The next thing that we need to do is we need to calculate the value of c, the constant of integration. And so the best thing to do is to plug in x equals 0. And so we're going to have the natural log of 1 on the left side, and on the right side, this is going to be 0 to the n plus 1, so 0 times anything is 0. And the natural log of 1 is 0, so 0 is equal to c. So we can get rid of this. And so we could say that the natural log of 1 minus x squared can be represented by this power series. Now there's more than one way to write a power series. So can we write this series in a way that looks more appealing? Let's find out. So what we're going to do is we're going to write out the terms of the series. So let's start when n is equal to 0. Negative 1 to the 0 power is positive 1, and positive 1 minus 1 is 0. Now when n is equal to 1, this is going to be negative 1 minus 1, and so we're going to get negative 2. And then this is going to be 1 plus 1, which is 2, so that's x squared. And then this will be 2 as well. Now when n is equal to 2, this is going to be negative 1 squared, which is positive 1 minus 1, and so that's going to be 0. So anytime n is an even number, we're going to get 0. Now when n is equal to 3, this is going to be negative 1 minus 1, and so that's going to be negative 2. And then 3 plus 1 is 4, so this is going to be 4 as well. And then it's going to be plus 0 minus 2x to the 6 plus 0, and then minus 2x to the 8 over 8. And then this will continue on forever. Now let's ignore the zeros. And what we're going to do is take out a negative 2. And so we're going to get x squared over 2 plus x to the 4 divided by 4 plus x to the 6 over 6 plus x to the 8 over 8, and so forth. So what we're going to do is we're going to write a new series that corresponds to the numbers that we see here. So we're going to say that n equals 0 for this term. Let me put it on the bottom. And when n is 1, we need to get 4. When n is 2, we need to get 6. When n is 3, we need to get 8. So how can we write a formula that corresponds to the arithmetic sequence 2, 4, 6, 8? We need to use this formula. A sub n is equal to a sub 1 plus n minus 1 times d. So when n is 1, we need to get an output of 4. So we're going to say a sub 1 is 4. And the common difference is 2. Each of these numbers, they differ by 2. And so this is going to be 4 plus 2n minus 2. 4 plus negative 2 is 2, so we're going to get 2n plus 2. So thus, we can write this series like this. We could say it's x to the 2n plus 2 divided by 2n plus 2. And we have a negative 2 in front. So you could represent this function in any of the two ways. But this one is better because it doesn't include the zero terms, which are just not needed. So this one is just more simplified, but both of them are correct, so keep that in mind. Now, what is the interval of convergence for this series? So keep in mind that series is based on the two geometric series that we had earlier in this video. In both cases, the common ratio is x. So x has to be less than 1, the absolute value of x, for both of these two series that we combined to get this one before we integrated it. So for both of these series, they will converge on this interval between negative 1 and 1. So when you integrate a series, the interval of convergence will be the same, with the exception that the endpoints may change. So if we were to plug in x equal 1 to this expression, we're going to have 1 over 2n plus 2. And will this series converge when x is 1, or will it diverge? Just by looking at it, if you take let's say the integral test, it's going to diverge. And if you plug in negative 1, you're going to get negative 1 to the 2n plus 2 over 2n plus 2. Now, negative 1 to the 2n is the same as positive 1, and negative 1 squared is also positive 1. So this will be the same. Using the integral test, that's going to diverge. Therefore, this function can be represented by this series only in this domain. Now let's make sure we have the right answer. So let's check the work that we have. So I'm going to make a table. So this is going to be x, and then ln 1 minus x squared, and then the value that we get for the series. So let's try 3 points, 0.25, 0.5, and 0.75. And notice what happens. The natural log of 1 minus 0.25 squared, if you plug that in, you should get negative 0.06454. Now the natural log of 1 minus 0.5 squared, that's negative 0.2877. And then ln 1 minus 0.75 squared, that's going to be negative 0.8267. Now let's see what we get if we use a series. So it's negative 2 times, the first one was x squared over 2, so this is going to be 0.25 squared over 2. And then it's going to be plus 0.25 to the 4 over 4. And then plus 0.25 to the 6 over 6. And then 0.25 to the 8 over 8. So we're going to stop at the first 4 terms. And we're going to see how good this approximation is. if we go on to infinity, it's going to give us the exact answer. But we're going to stop here. So go ahead and type this in. And don't forget to multiply everything by -2. So you should get -0.06454. Now go ahead and plug these values in as well, using the first 4 terms. So I got -0.2874 as opposed to 77. So it's a little bit different, but it's still pretty close. Now let's do the same when x is 0.75 for the first 4 terms. So this is -0.8051. So what do you notice is happening here as x increases from 0.25 to 0.75? Notice that the accuracy decreases when n equals 4. Now you can make this answer more accurate. You simply need to increase the n value. So if you add a few more terms, it will converge to this number. So the power series that we have is correct. But let's talk about the trend that we see here and why that's happening. Now, we said that the interval of convergence is -1 to 1. And it's centered at 0 because 0 is the midpoint between -1 and 1. So let's plot the interval of convergence on a number line. Now, the reason why it's so accurate at 0.25 is because 0.25 is very close to the center of where the series converges. And that is why we do not need to add so many terms in order to get a very good approximation of the true answer. Now, notice that when x is 0.75, the accuracy decreases. As we move away from the center towards the edge of where the series converges, in order for us to get an accurate answer, we need to add up a lot of terms. So to summarize all of this, as x approaches the center C, the number of terms that we need to get a good approximation decreases. Now, if x were to move away from the C value, or the center, then the number of terms that we need to get a good approximation increases. So if x was like 0.95, we need to add up a lot of terms to get a good approximation. If x was like 0.1, we won't need to add many terms to get a good approximation. And so we're going to end it right there. And that's all I got for this video. I hope you found it to be helpful. Thanks for watching.